So hey guys, it's Michael with Breaking Concepts again, and today we're going to take a look at this mutation accumulation question. Basically, it's from the chapter of application of differentiation. So what we're going to use is the mean value theorem, right? Different other application theorems of different derivatives. So be prepared in order to use this to solve this question. And also the Jensen's inequality. So I'll go ahead and take a pause of this video. I'm going to hide myself and just give this a go and see if you can do it. Okay, so I guess you guys have tried it yourself, and remember I kind of mentioned about Jensen's inequality. Well, actually, it's a super helpful concept that I actually made a video yesterday explaining the concept itself. So today we're gonna skip through the logistic of it, but it's a super quick video I made. I think it's around like 5 minutes. So I'm gonna put the link down this description so you guys can click it to check it out. Or if you already have a concept about what is midpoint Jensen's theory, inequality, and then be my guest, enjoy this video. So first of all, let's take a look at this question together, right? So it says mutation accumulation, okay? So when a population is subjected to a mutagen, right, the fraction of the population that contains at least one mutation increase with the duration of the exposure. Okay, so what that means is basically, well, you have a guy. Let's say you have a population of 100, and maybe one guy got contaminated, and so the fraction becomes 1/100. And as time goes, as time progresses, that fraction can kind of go bigger and bigger and bigger because everybody started getting contaminated, right? Same thing happened, with the pandemic, whatever, and whatnot. Right, so that's basically what happens, and what they're saying. And it says a commonly used equation describing this fraction is ft equals to 1 minus e to the power of negative mu t. Okay, where mu is the mutation rate. Mutation rate, get it? So anyways, and it's positive, and suppose we have two populations, right? A and B, and population A is subjected to the mutagen for 3 minutes, whereas with population B, half of the individuals are subjected to the mutagen for 2 minutes, and another half for 4 minutes. So which population will have the largest fraction of mutants? Okay, explain your answer in derivatives. So we're going to use the Jensen's inequality to solve this question. Jensen's inequality. And to use the Jensen's inequality, right, which is also we're going to use the derivative, we're going to need the mean value theorem. Okay, so if you're not understanding or you're not familiar with mean value theorem, I would highly encourage you guys go to check it out. So to use the Jensen's inequality, so you want to know if the curve is concave up or concave down. Okay, so that's super important. So now so let's look at the equation itself. Ft, right, which gives a fraction of mutant is 1 minus e to the power of negative mu t. And so we know that the e to the power of negative x is going to look something like this, right? Yeah. And then if you have a minus here, what that means is, okay, you're flipping everything, right? Reflecting, about the x-axis, right? So you have e, negative x, right? So what that's going to look like is a reflection that goes like this. So right off the bat, you can see that, oh, this is kind of like a concave down curve, right? So, but we have to prove it. And the way we prove it is super simple. We just take the derivative twice. And differentiating this is super simple. We just use the chain rule. F prime t is equals to negative e negative mu t, and then times our negative mu, right? Negative mu times negative is going to be mu e negative mu t. Okay, this is our first derivative, and that doesn't really give you the concavity. It just gives you like the the rate of change. So we got to do it again. So you have mu e negative mu t times our negative mu. So now you have negative mu squared e negative mu t. And so we know that mu, again, this is positive, this is positive, this is positive, and so the entire thing is negative. So negative, so we know that f prime x is negative, and so we can just kind of prove that, okay, it is a concave function. Right, it's going to be negative wherever we go, so it's a concave down function. Sorry, concave down function. And now we know that it's concave down, so we can start with the Jensen inequality. Well, first of all, let's draw a graph first to help you kind of visualize what's going on. So we know it's going to be something like this. It's increasing, but it's concave down. So now it was given that population A, I'm going to use for the green pen, population A, right? We expose the population A for 3 seconds, right? Somewhere here, right? And 3 is our input, right? Our time, and our Y is our F, which is our fraction of mutation, right? So whenever we have this one, right, our F3 is the fraction of mutation at time t. But interestingly, our population B, and just for clarity, I'm gonna write F3 because that gives you the fraction, okay? So I don't want you guys to get confused. And so now we have F2 plus F4 divided by 2. And where do we get this from? Because we know from our question, well, half is going to spend on 2 minutes, half, and then the other half is going to spend on 4 minutes. So that's why we have F2 plus F4 divided by 2. So looking at the graph, we have 2 here and we have 4 here. We want to know, well, first let's try and find F2. F2 is going to look something like here. It's going to be lower than F3, obviously. And we have F4. F4 is going to be here. F4 is going to be somewhere along the lines of here. Right, and then there we have F4. If we add these points together and divide by 2, that's the fraction total for population B. Okay, so not just these two numbers. We gotta divide by 2. We're gonna add them up and divide by 2. The $1 million question is gonna be if the population A is gonna be the fraction of the population A is gonna be bigger, or the fraction of population B is gonna be bigger. Right. This is the question. This is the blank that we have to fill out. Okay, and we're gonna fill this out at the end of this video. So the question is, how do we do that? And here is where we get in the Jensen's inequality, because we already know that, we proved that the entire thing is concave. So now all we gotta do, I'm gonna use another graph just to show you clearly where and how we can use and leverage mean value theorem. So with 2, 4, and 3. Okay, so first of all, notice one thing. 3 is equals to 2 plus 4 divided by 2. I know, super intuitive, but this is important because because 3 is our midpoint between 2 and 4. And so we want to divide the entire graph into 2 parts, right? The first part, the first half is from 2 to 3, and the second half is from 3 to 4. So we want to do something like this, okay? We want to draw a line here and here, okay? Just kind of go across here, right? This is the average line. Right now we can use the mean value theorem. So we can get like a C1 here, a C2 here, and C1 and C2, looks irrelevant, but it's actually super important, and we're going to see that in a bit. So first of all, we know that by our mean value theorem, we know that F prime C1 is going to equals to our F3 minus F2, right? And then our 3 minus 2, okay? And so for this one, we also know that for F prime C2 is going to equals to, okay, let me just put all these here, is going to be equals to our F4 minus F3. Okay, and then we know that it's going to be 4 minus 3. Okay, this is mean value theorem. Look at here. This is simply the mean value theorem, okay? And this is going to kick in clutch in like a couple of seconds. So first of all, let's just move the things to here, right? Okay. C1, 3 minus 2 is equals to F3 minus F2. Okay, same thing here. F prime C2 is times 4 minus 3 is going to equals to F4 minus F3, okay? So here, what we know, first of all, well, 3 minus 2 is going to be equals to 4 minus 3, right? Same thing, equals to 1. But here is where the difference is. The difference is here. Okay, so, well, we know C2 is going to be greater than C1, obviously, right? But because it's a concave down function, we know that our C1, the slope of C1 is going to be greater than the slope of C2. So we know that, I'm going to use a different pen, F prime C1 is going to be greater than F prime C2. And so what this gives us is that, okay, this equation is going to be greater than this equation because of this. So we have F prime C1 times 3 minus 2, and then it's greater than F prime C2 times 4 minus 3. Okay, so what this means is that actually it means this. Okay, our F3 minus F2 is greater than our F4 minus F3. Okay, and so you want to make this over here, and you'll get F3, 2, and then you have F2 plus F4, right? And then what you're going to have is F3 is going to be greater than F2 plus F4 divided by 2. So there you have it. So we just prove that the fraction of population A is greater than the fraction of population B. So here is our answer. Our answer is going to be this. The fraction of population A is going to be greater than the fraction of population B. I hope this makes sense to you guys. It is a super interesting question. When I first do it, I actually try to find the difference and trying to calculate this and that, but this is not what we're looking for. So I hope this makes sense with you guys, and please stay tuned. Leave a like, leave a comment, and stay tuned for the next videos. Thank you so much. Have a great day. Bye-bye.